After the definition of Gauss theorem, now we are going to start with the applications of Gauss theorem. Now Gauss theorem was established to ease down our calculations, our derivations for various distribution of the charges to find the electric field intensity due to any of the distribution of the charge. The first example which we are going to take is of the infinitely long straight uniformly charged wire. Now it is similar to that charge distribution, linear charge distribution, if having the same charge density lambda over here, because it's a linear charge distribution. Now if we go with the previous method which we used to follow for the distribution of the charges, we'll first apply the Coulomb's law and find the force, and then we'll put in the formula for the electric field intensity, and then we'll find the electric field intensity. So it is going to be a little tedious method. Now we are going to apply Gauss theorem for this same situation, and we'll see the same results here. Now, how to apply the Gauss theorem? The very first thing is to use a convenient Gaussian surface here. Now, what is a Gaussian surface? Gaussian surface is an imaginary regular surface. Now, if I use the word regular surface, means that whose area formula is known to us. If we take any irregular shape, irregular surface, then the surface area needs to be found out, and it will become again a difficult task. So now we'll be taking this scene here, this case here, having a long straight wire. So a long straight wire, so the best suitable surface over here is a cylindrical surface. So now we are having a cylindrical surface which I name as a Gaussian surface here. I have taken the cylinder because I know its surface area. So now the positive charge are along the axis of the cylinder whose length is L. So electric field lines will be perpendicular to it, because we have done earlier also that the electric field lines, they always start from the positive charge. So they will be perpendicular to it. So I have drawn on both the sides, upwards and downwards, so that the electric field direction is clear to you all. Now we are having three surfaces, 1, 2 and 3. First surface is having area in this direction, second in this direction, and third will be having the area in this direction. Right, now I'll be finding out the flux due to first, second and third, and then we'll take the total to find out the total electric flux. So if you see for the surface 1, flux will be E dot S1. So E is in this direction and S is in this direction, so they are making angle 90 degree, so it becomes 0. Similarly, for the second surface, it again becomes 0 because they are making angle 90 degree with each other. And third surface, here surface is in this direction and also the electric field intensity is in the same direction, so they are making angle 0 degree. So it becomes ES3, and curved surface area of a cylinder is 2 pi RL. Right, so this is the total flux I have got. So total flux is phi 1 plus phi 2 plus phi 3. So this is 0, this is 0, and it becomes E into 2 pi RL. So this is the left hand side of Gauss theorem. Gauss theorem said phi is equals to Q upon epsilon naught. So left hand side we have done. Now let's work on the right hand side. Right hand side says Q upon epsilon naught. Now Q is the charge in this area. Now there is a surface charge distribution, linear charge distribution, sorry. So linear charge distribution means Q can be expressed as lambda into L, because lambda is Q upon L. So Q can be written as lambda into L. Right, now we are having one is this equation and the second is this equation. Now Gauss theorem says that first equation and second equation should be equal to each other. So we know that phi is equals to Q upon epsilon naught. Phi from equation 1 we have obtained 2 pi RL, and Q upon epsilon naught from equation 2 we have obtained lambda L upon epsilon naught. Right, so L and L they cancel out, so you get E is equals to L upon 2 pi epsilon naught R. Right, so this is the relation for the electric field intensity, and we say that E is inversely proportional to R. Right, now if lambda is greater than 0, then E will be outwards. This is what we have taken. Lambda greater than 0 means the charge density is positive. positive charge is there. If lambda is less than 0, so E will be inverse. So it is not necessary to always take this charge distribution as positive. We can take negative also. Correspondingly, the direction of electric field intensity will be there. So this is the relation we have obtained for the linear charge distribution. Now one question which comes here is, we have taken infinitely long straight wire, but we have not taken the finite length. Why we take infinitely long? Because infinitely long we take so that we can delete the factor of the edge effect, or it is also known as the end effect. Because at the corners of these charges, these will be doing further also in the next topics. So at the end of this, the positive charge will be having the electric field intensity in all the directions, right? Because it always starts from the positive charge. So to eliminate this, so that the total electric field intensity is not hampered by this effect, so to eliminate this effect, we just take the infinitely long straight wire, so that the ends, they do not contribute toward the increase or decrease of the electric field intensity. So this is kind of an ideal situation which we opt for.